Hello and welcome to today's webinar. My name is Hee-Soo Lee and I'm the product owner for PathWave ADS, SerDes and DDR products here at Keysight Technologies. We have some great content prepared for you today, which will be followed by a question and answer session. So please feel free to submit those questions at any time during my presentation. Let me start my presentation starting with the agenda. First of all, I'll go over the design and simulation challenges for electrical, optical, electrical, or simply EOE systems. Afterwards, let me walk you through the details of an integrated EOE workflow. Then I will discuss PAM4 and TDECQ measurements, followed by a short demo. Okay, let's get started. As you know, data centers transport a vast amount of data and the demands continues to grow. Then the question is, what really drives this growth? As you can see, cloud-based services, video streaming, Internet of Things, 5G connectivity, and more are making headway with the demands. This really puts a strain on communication networks and network infrastructure, in particular data center interconnects, which is also called DCIs. They must evolve and transform to support these demands. Therefore, this really leads into today's optical technology development for DCIs, to really offer overall network simplification, greater capacity, as well as power reduction. However, these technology trends and evolutions bring hardware design engineers a headache because the design itself, it goes through multiple domains. For example, it starts from electrical, but going through the optical and coming back to electrical, it just crosses multiple simulation domains. If the design engineers design a subsystem inside an EOE system, how does he or she really evaluate the true performance of the subsystem? I believe one should consider the subsystem's performance under the entire link in order to truly understand and evaluate the electrical or optical system's performance. Let me get you a bit more details on the real challenges with specific questions such as, can electrical design engineers analyze the entire link from electrical to optical back to electrical, passing through different domains? Another one is, can transceiver design engineers simulate the electrical design for a given BER target, such as E2-6, within the system? Can electrical system engineers characterize the transceiver performance with varying optical design parameters, such as length of fiber or laser power? Let me introduce the industry-first real-time analysis method using PathWave ADS Design System and VPIphotonics TransmissionMaker. This method predicts a design margin such as eye height, eye width, and BERs at the desired system BER. Let me show you how you get those challenges resolved. Here is an example that I want to use to understand a typical EOE system. The picture to the left shows the system architecture of EOE system. The picture to the right shows physical implementation of that system. As you could see from these pictures, you can see that it combines two different domains, one electrical parts and the other is optical parts. For electrical domains, there are a lot to evaluate or simulate, such as modulation format, pulse shaping, going through ADC or DAC, or DCR, equalization, and forward error correction, and so on. For optical domains, there are different matters, including a light wave generation or detection, and going with the modulation, and doing the muxing or demuxing, and in analyzing the performance of fiber transmission, and going with the pixel, and so on and so on. Typically, all the problems or measurements for electrical domain were done by EDA tools. For optical domain, PDA tools, which is called photonic design automation. But since the signals are going through different domains, we really need a solution that deals with electrical and optical at the same time. This is where EPDA solution is required. So now the question is, how do we handle these complicated and difficult problems? Let me just get to the solution. I'm going to start with first a challenge, which is being able to simulate the entire EOE mixed domain design challenges. Actually, this slide shows the answer to it. The schematic shown here is the complete EOE system, which consists of electrical and optical and electrical part of the designs. The transmitter shown to the left, which is TXAMI, generate PAM4 signal, and this signal goes through electrical channel and then passing through optical channel, then coming back to electrical channel. This is what we just call the EOE system. With the PathWave ADS and using channel simulation technology, now design engineers are able to simulate this entire link to evaluate eye diagram, eye height, eye width, and other important measurements at any locations in the design. For example, at the redriver output and right after the optical channel and the receiver output. You can simply put eye probe wherever you want to measure those data, and you'll be able to see the result, like the result shown in this slide. To the second challenge, which is being able to simulate the electrical design for a given BER target within a system, these plots demonstrate the solution. The 3 rows shows the results at different number of simulated bits, which were 8,192 number of bits. Second, 1 million, and the last was 10 million bits, which is equivalent to 1e⁻⁷ BER level. Now you can see that the eye size is getting smaller with more number of bits simulated, which is the expected behavior. The last column that really shows multiple results of BER contour, timing, and voltage bathtub. Now the transceiver design engineers can truly evaluate the design under the given target BER with this solution. Last but not least, the new integrated EOE workflow allows electrical design engineers to optimize the electrical design under different optical design parameters. In this example, as you see here, the length of optical fiber and the laser power are swept from 1 kilometer to 5 kilometer, and the other from 4 milliwatt to 8 milliwatt respectively. We know that 200 gig base FR4 supports at least 2 km over single mode fiber using 4 parallel wavelengths each at 50 gigabit per second. But the question is, how far this can go? Or how far can the system support? Can we analyze the performance variation with them? What is the really adequate laser power level to maintain a good eye opening? Can we really predict the performance variation? As you see here in the results, the integrated EOE workflow solution really enables all of these. That's really, really good news. Now you may wonder, how does this work and what the details behind the scene? Keysight developed the industry-first integrated EOE workflow by partnering with VPIphotonics, who is the leading PDA vendor in the photonic market. We wanted to deliver the industry best solution by using the best-in-class simulation technologies to eliminate any of key design barriers to the development of high-performance data center products. As we discussed in the previous slide, the solution is really designed to address the 3 design simulation challenges, starting with being able to simulate the entire mixed domain problems. Second, being able to observe system performance variations with varying optical design parameters and really designing the system targeting for a given BER specifications. As seen in the schematic here, the optical design is represented by the ball, which is called a VPI optical link component in PathWave ADS, where the optical design parameters are revealed to electrical design engineers. Therefore, the optical design can be easily dropped in and simulated within the entire link. Let me talk about a little bit on VPIphotonics. VPIphotonics is the leading supplier for optical and photonic design automation. They really have a long history of serving the market, more than 20 years. VPIphotonics offers professional software for a lot of different applications. That includes waveguide and fibers, integrated photonics and optoelectronics, fiber-based lasers and amplifiers, optical transmission system and networks, link engineering and equipment configuration, and so on and so on. Top of it, they do also offer design services and technology consulting for a lot of different application areas, including telecom and datacom market, as well as the sensing and analytics. So they have in this market and seen as a simulation expert, more focused on the optical and photonic markets. They are located in Berlin, Boston, and Minsk. Now let's take a look at the details of an integrated EOE solution process. First of all, EOE code simulation is driven from PathWave ADS using ADS channel simulation technology. The optical designs, which is basically VPI's .btmu design file, is accessed by the ball components in ADS. Inside of the VPI design, which is the BTMU file again, designers need to place input from ADS and output to ADS I/O modules that literally connects VPI designs to ADS and vice versa. The simulation process for this integrated EOE workflow is not static but dynamic process. That means instead of importing and exporting data files between the two, ADS actually directly calls VPI design suite to process the electrical signal through the optical channel and return it back to ADS. in a very interactive manner. This simulation process continuously runs until all simulation bits are consumed, which really takes the simulation accuracy to the next level. The simulation bits from ADS to VPI and VPI back to ADS are set by block size. The default number for this block size is 1024. However, this number can be changed based on the user's need. With this flow, you don't have to read in or redefine optical design parameters from VPI design suite. The optical design parameters from VPI are automatically picked up and displayed by the bulk components as we discussed. This is how the parametric analysis can be performed with varying optical design parameters in ADS. This really enables electrical and system engineers to sweep or batch simulation to do parametric analysis for the evaluation of system performance variation to the optical design parameters, such as laser line width, RIN, SMSR, chirp, MPN, single mode fibers attenuation, dispersion, and so on and so on. Here is an example that really shows 400 gig base FR, for example, using EAM driver and single mode fiber running at 56 gig PAM4 signaling. Inside of a VPI designs, users will be able to put a VPI analyzer. Then designers will be able to visualize any results coming from this optical channel simulation, including optical spectrum data and eye data, and so on and so on. However, if design engineers wanting to do some special measurement, such as TDECQ or ER, which is extinction ratio, or even outer OMA, if these measurements are required, designers can send the simulated waveform from ADS directly to FlexDCA using a FlexDCA probe shown in this ADS schematic. Therefore, not only being able to see all the eye data or BER or bathtub, user will be able to analyze all the simulated waveform exactly same as the measurements done with rear device. So the user, they don't have to scratch their head thinking about what algorithms are used for simulation, what algorithms are used for the measurement, is because they are using the same measurement platform to measure certain specific data, including TDECQ or ER, as well as the outer OMA. Lastly, I would like to quickly go over PAM4 signaling and TDECQ measurements in the next two slides. NRZ, non-return to zero, as we all know, has been a main signaling technology for many different applications. Nowadays, PAM4, which is pulse amplitude modulation 4, is a very common signaling technology in Ethernet applications. The question is, why PAM4? PAM4 has its own advantages as well as disadvantages. One of the main benefits of PAM4 is having 2x throughput, using the same channel. In other words, PAM4 allows design engineers to develop products to fit cost structure of available channel technologies. Going into a little bit more detail, the Nyquist frequency is 1/4 of the bit rates. So if we are using the 53 gig data rates, then Nyquist frequency would be 13.2 gigahertz. That means we don't have to worry too much about higher frequencies. It's because the Nyquist frequency is low, therefore we'll be able to use the channel we have been using for other data rates without having much of problems. However, since it has basically 4 levels, it has its own disadvantages, including how do we recognize which levels are meaning what a symbols. In order to analyze it, the TX as well as the RX system goes a lot more complicated. In other words, it raises the cost of the design without having any question. Since there are more levels, it makes the system a little bit more susceptible to amplitude noise. That is another downside of the PAM4, but again, the gain from PAM4 is a lot bigger compared to those downside. Therefore, PAM4 became a kind of standard, signaling, especially in Ethernet applications. Finally, let me talk a little bit more on the FlexDCA for TDECQ. Using FlexDCA probe, any of ADS users, including integrated EOE workflow solution, designers will be able to send simulated waveform directly to FlexDCA, where they can make up the all different type of the measurements, including the TDECQ, outer OMA, and ER, and so on and so on. This really connects simulation domain to measurement domain. This also enables design engineers to perform compliance tests on the simulated waveform. You can find the various different compliance apps with the FlexDCA and apply those compliance testing to the simulated waveforms. This ADS to FlexDCA connected flow works on FlexDCA offline, which is installed on the local machine, but also it works with the remote hardware or any of FlexDCA software connected over a network. All right, now let me switch the gear and do a quick demo. For my demo, I'm using ADS 2020 Update 2.0. Let me start my demo with the first schematic, which is exactly the one I have been using for my presentation. Left side of the design is basically electrical design, and in the middle there's optical channel, and then the other side there's electrical design. As we discussed, we are using TX-AMI to generate the PAM4 signals, and that signal goes through PCB data, which are basically represented by S parameter data. And then there is a redriver that drives the optical channel. If you want to see what's inside this optical design, which is basically both components, you can double click it to see the details of it. As we discussed, all the optical design parameters coming from BPI BTM new design are shown here. That includes a fiber length, laser power, EAM bias, and so on and so forth. As you could see, file path is pointing to BTM new file, which is the design file from BPI. And if you want to see that, you can go and then browse it and find the file, then open it. When you click this open button, it opens up the BPI design suite. As we discussed, in order to make the connection between VPIphotonics to ADS, you really need to have ADS dynamic input and ADS dynamic output I/O modules that connects VPI design to ADS design environments. As you can see, there are all optical design components that includes a single mode fiber. If you want to see the more detail, you can double click it to see these components, which is showing all the necessary optical design parameters. Same for these photodiodes and any of EAM drivers. I can go back to ADS. From this ADS, what I could do is basically setting up the iPro where I want to make the measurement, one at the redriver output and right after the optical channel as well as the receiver output. Again, the channel simulator from ADS that drives the entire simulation, and right now the number of bits for design is set to 8,192. So I'm going to just go ahead and run the simulation. Okay, the simulation is done. The simulation took around 37 seconds for 8,192 bits. Now you see that all I diagram data, one right at a read driver output and the other is optical channel, and then output data of the receiver with CTLE equalization applied. This data shows BER data along with timing and voltage backup. For the higher number of bits, such as 1 million bits and 10 million bits, the results are shown here, which is the one we examined during my presentation. Okay, next I'm going to show you the schematic for parametric analysis. The schematic looks pretty much the same as before, but the only difference is the setup for parametric analysis. In this case, I made the two variables, one for fiber length, named as FL, and laser power as LP, and I was sweeping through these two design parameters, which is the one coming from a VPI design suite. Setup for this is pretty straightforward. You just need to do parameter sweep, one for LP and the other for FL, and then just go and then run the simulations. In this case, I set up the design variable for fiber length from 1 kilometer to 5 kilometer, and for laser power, I set power level from 4 milliwatts to 8 milliwatts with a step size of 1 milliwatts. With this example, I won't simulate it, is because there are 9 cases for fiber length and 5 cases for laser power, so that the total number of simulations to be run is around 45, which takes quite a while. Therefore, I won't simulate, but let's go and then examine the results. By the way, the sim time for these 45 cases with 8,192 bits took around 30 minutes. Okay, here's the results. The two eye diagram, what we are seeing, one at optical channel output, which is directly from VPI simulations, and the other data is basically RX output eye diagram with CTLE applied. The current set for laser power is about 5 milliwatts, and the fiber length is set at 2 kilometer. What if we pick this up and move to longer a fiber length, such as 4 kilometer, and we can easily see eye gets smaller. What if we increase the laser power from 5 milliwatts to 7 milliwatts, then we can see that eye gets bigger. This is very easy to understand. You can examine the performance data by varying fiber length. For example, like moving to a smaller number, you can just pick up the arrow button of your keyboard and then just move through it. Then you'll be able to see all the changes coming a more interactive way with ADS data display by doing this parametric analysis. Not only being able to see this eye data, ADS offers the data for eye height and eye width at certain BER level. In this example, I set the BER level at 1E2-6. Then all the values what you are seeing is the value at this BER level. Top of it, ADS offers VSR PAM4 measurements so that you can measure all specific measurement data under VSR PAM4 specific measurement. Lastly, I'd like to demo how you use FlexDCA probe to make TDECQ measurements for any ADS circuit, including this EOE system. This FlexDCA probe is scalable components. What I mean by scalable component is basically you can change the number of channels based on your needs. And then FlexDCA probe automatically scales number of pins. Here is an example. If you change the number of channel to 4, then there is the channel number 3 and 4 are generated. And then you can set up the other signal type, either differential or single-ended. And when you go and then apply it, then it makes more pins with that components or symbol, right? In this case, we wanted to use only 2 channels, one for optical channel output, and the other one is picking up at RX output. We'll be just going back to 2 channels. In this example, again, we are using the other RX receiver with a CTLE enabled. Let me show you how you enable the CTLE. You open this receiver and there are choices you can make. You can enable the CTLE or you can enable DFE and so on and so forth. So if you want to set up the specific CTLE, you go and click this edit button, then it brings up the CTLE visualizer where you can define the DC gain and poles and gyros and so on. ADS provides a preset values for Ethernet applications such as IEEE 802.3bs and also CI 56 gig VSR, NRZ. All different type of CTLEs are supported, including MIPI standard. So in this case, I chose a 3dB CD-AOE CTLE, but if you want, you can change it to different value. With that change, it shows the frequency response as well as where is the poles and gyros along with what those values are. This is how I set up this RX. And let's go then run the simulation. The simulation is running. What happens once the simulation is finished? We'll be picking up all the signals from these 2 nodes and send those waveform data directly to FlexDCA. During this process, it is automatically starting a FlexDCA and populates ADS waveforms into designated slot or memory channels. Alright, it took around 1 minute, and now we see that FlexDCA is populated with the waveform data coming from ADS. Alright, let me show you how you make TDECQ measurements. Let me go to the math. In this math function, I switch it to signal processing, and I see TDECQ equalizer. I drop that in, and I put the input signal, which is basically 2A, into the input of this TDECQ equalizer. Then output of this TDECQ equalizer, there will be F1. So let me open this TDECQ equalizer and select the IEEE 802.3 final. Then we'll be applying this TDECQ equalizer to the signal of 2A. So from here, let me go back to the main window and enable this F1. Then this F1 is the results of the signal of 2A with the TDECQ equalization. Then I can make the measurements. Switching to this PAM4 measurement, I go and click the this TDECQ. Then I choose F1. Then we'll make the other TDECQ measurements and give me the data of TDECQ. What about making another measurement for jitters, which is very straightforward and easy. You just need to switch it to the modes from eye mask to jitter. Then you can apply all the jitter measurement to the selected signal, and FlexDCA will automatically calculate and give you all the necessary information, including eye width, eye heights, and skew, TJ, DJ, RJ, and all those numbers. All right, this ends my demonstration. Now let me summarize my presentation. As we have discussed, the PathWave ADS and VPIphotonics EOE solution enables the design engineers first to simulate the mixed domain electrical, optical, electrical system problems. Second, to observe the system's performance variation dynamically with a change in optical design. Third, to evaluate the electrical subsystem's performance in a system for a specific BER target. Also, ADS to FlexDCA connected flow makes TDECQ and other advanced PAM4 measurement easy. By the way, if you are interested in getting the demo project files, please contact me directly at he-su_lee@keysight.com. Finally, I also want to acknowledge the support of my partners at VPIphotonics. Thank you.
Okay, thanks so much, Hee-Soo. All right, now it's time for the question and answer section. All right, Hee-Soo, got lots of questions for you. So here's your first one from Tony. Okay, so this is a very interesting topic, and thank you so much for sharing this. One question, though, is whether this solution can be applied to SPICE-like transient simulations.
Well, that's a very good question. The answer to the question is simply not yet. This is the first solution release, so we only targeted the solution for the system or entire link level. But we do have a plan to move the solution to the next level, including the transient engine in the future.
Okay, right. Thanks. And then Elizabeth asked, and then there was another question by Hao Zhang. Elizabeth asked, does this EOE solution require any special license? And Hao Zhang also asked, do we need an extra license for VPIphotonics?
Yeah, thank you for the question. It requires actually 3 licenses, 2 from Keysight and 1 from VPI. For Keysight, you basically needed to have the channel simulator and VOL, which is VPI optical link licenses. From VPI, you also need the license, which is called a TransmissionMaker license, to be able to run this EOE solution or simulations.
Great. Here's a question from Giancarlo. ADS to FlexDCA solution looks very interesting. Do you have a similar capability with the Infinium scope?
Yeah, not as of today, but this is the one feature we are working on for ADS 2021, which is the one scheduled for July release this year. So you will see this capability coming very soon. Thank you for the question.
Here's a question from Mo. Can we run the simulations you showed with previous versions of VPI, assuming we have all of the files?
Yeah, that's another excellent question. Currently, this solution supports VPIphotonics Design Suite version 10 and 11. So if you happen to have any of the designs coming before this release, like version 10.0, the solution may not support that whole designs. So please make sure your design is basically converted to VPI Design Suite 10.0 or 11, then you should be able to run or be able to simulate the EOE link. Thank you.
Sure, thanks. Here's a question from Erdal. Actually, submitted 2, but it's almost the same thing. So we have another solution, our silicon RFIC solution, Golden Gate. So can the solution be integrated with Golden Gate? Will it work with Golden Gate is the question.
Yeah, this is quite similar the first question, whether we'll be able to run the SPICE-like a simulation for this entire EOE link. As you know, Golden Gate is more like a circuit-level simulator, but the solution what we developed as the first release is targeted for EOE, which is the entire link or system level, so that bring the Golden Gate into this flow may not work at this point in time. But in the future, we'll be looking into the other, multiple ways of bring different engines to be able to state or analyze all the necessary EOE related or EO or OE related design, challenges. Thank you.
Great, thanks. Sorry for the audio back in my background. Tariq asked, many times electrical driver need to be adjusted for nonlinear compression of EO devices. Does ADS-AMI support the mechanism to adjust PAM forward levels independently?
Yeah, that's another very interesting question. If you remember the design project I just demonstrated that has a TX AMI that generated PAM forward signals. However, in the middle there is a redriver, which is actually pointing to another AMI motor. So if you want to adjust any of power level or signal level before it hits optical channel, then you should be able to handle those variations through the AMI motor. But again, interesting part is the AMI motor is not part of ADS. AMI motor is the one coming from the chip vendors, so that as long as the AMI motor from the chip vendor allows you to lever up and down the signal levels, then ADS should be able to handle it properly. Thank you for the question.
Sure, yeah, thanks, Tariq. Murdad has some more questions, and they're great questions, and it might be a good idea to contact him directly, too. So let me ask you. Okay, thanks for your previous answer. How about X-parameter model for circuit to be integrated with solution? If not, how can a full model of the circuit be implemented in the EO full link?
Yeah, this is a similar kind of question dealing with the other different engines for the solution. Right now, the solution again is designed and targeted for basically channel sim. Channel sim is not like the other circuit simulator. As you probably remember, X parameters are the one basically designed for a circuit level simulations. Therefore, at this point in time, again, at this point in time, not the future, our solution is limited to the channel sim, which means we may not be able to handle the X parameters in the design properly at this point in time because that is channel sim again. Thank you.
Sure, and here's a question from Joel. I'm hoping I get it right. Okay, technically, I'm more interested in E to O or O to E instead of EOE. Does the solution address EO and OE problems?
This is an excellent question. Currently, the solution, as I mentioned, was designed for EOE. However, it doesn't mean that you can't simulate or as I used in my presentation, the example, and then talked about it, you can measure the optical signals within VPI designs with VPI analyzer. Therefore, you can send the electrical signal to VPI and get the output data with a VPI analyzer. Then that becomes more like an EO problem. And when you put the VPI analyzer and get the output data and ADS, then it's more like OE, kind of problems. However, there is a downside of this solution, which is not being able to interactively exchange the data from VPI analyzer to ADS or vice versa for other simulation needs. Therefore, you will be able to simulate it, but the design solution is not letting you interactively exchange the all proper simulation result or data between the two. That's the one limitations. Although we have to cope with this limitation as of today, but we do have a plan to work on the dedicated EO and OE solution in the future. So please stay tuned with new solutions coming out from Keysight. Thank you.
Great, Hee-Soo. And let's take this last question from King. When will the new 112G VSR PAM4 be implemented in PathWave ADS?
Yeah, I think this is a little bit tough. Again, 112 gig PAM4, not much different from the PAM 56 gig PAM4. Again, the transmitters and receivers are coming from the chip vendors. So we have seen or interacted with multiple chip vendors who already developed 112 gig PAM4 AMI models. So within ADS, there's no limitation or challenges or problems to be able to simulate 112 gig PAM4 signals. It's just a matter of who is the chip vendors provide those AMI models. So the answer to that question is yes. However, one thing I guess you are asking for is whether Keysight can provide any generic 112 gig PAM4 models. The answer to it, yeah, we can provide the PAM4 models that works up to 112 gig, but that is not part of a standard product. So later on, if you are really interested in getting the model, then we can actually use the 56 gig PAM4 and extend the data rate, or moving the data rate higher to the next level, which is possible. But again, there is no standard AMI model we are providing to customers, but you can contact us, then we can work it together for making data PAM4 models that works up to the 112 gig. Thank you.
Thank you again for attending Evaluate Electrical Performance in Electrical, Optical, Electrical Link Systems, brought to you by Keysight Technologies. Please visit us at www.keysight.com/find/events for a list of upcoming events, and we hope you have a great day. Please stay well.